The talk will be on post-quantum security, and I will give you some insight. What are the threats that quantum computers bring to the table? And I begin to recommend some strategic actions that you should take in order to protect you and your enterprise yourself. So I will resample what is the current state. I will remind you what classical cryptography is and what is at its heart. Then I will bring to you the nature of the threat, quantum computing, how you could defend against the upcoming powerful quantum computers by introducing post-quantum cryptography, and give a little glimpse of the strategy how to become quantum safe. The first thing is, what is classical cryptography? And the first thing is RSA. RSA is a standard that is centered around prime numbers, right? So the public key that you have is a product of prime numbers, it's a large prime numbers, and you keep the prime number secret. And the private key is computed from these prime numbers by a well-known algorithm, that's in the private key. And if the prime numbers can be computed, then you can crack the private key very easily. That basically means if you can compute prime numbers of a huge number, then you can crack a private key, which is what we don't want. And there is an algorithm to compute prime number. We call that factorization, the prime factors. That is the breakage of RSA. And all known classical algorithms are exponential. That means they run for a very, very long time. And this is why we consider RSA secure. For example, RSA 2048 has been designed so that you need on a supercomputer the lifetime of the universe to crack it. This is a long time, right? This is why we think we are safe. And there's also DSA, you heard that very briefly. DSA is a digital signature algorithm. It uses different algorithm, but mathematically DSA is on the very same problem, namely computing what is called discrete logarithms. So factoring a number in prime factors is also something that computes discrete logarithms, and DSA does the very same. And if you want to compare DSA and RSA, so they are doing similar things, but RSA, as you know, is more used in asymmetric encryption, decryption, and DSA is a signature standard. Now, come on. And if you want to protect data or a certain communication, it all depends on the size of the key. The longer the key is, the more secure is your data and the communication. And because RSA 2048 is already a long key, so a lot of effort has been spent decades ago on reducing the size of keys while protecting the same level of security. And this is where elliptic curves comes in. An elliptic curve has this kind of shape, and you see above the equation of this kind of shape. And why is elliptic curve something that can do encryption? Very simple, because you can perform computation on this elliptic curve, right? So what you can do is, for example, if you have 2 points and you want to multiply these 2 points, you take a line through the points, it cuts the curve here, then you mirror it on the x-axis, come on my friend, yeah, and then you get the product, p times q. And if you want to square a point p, you take the tangent, right? The tangent intersects the curve, you mirror it again, then you get p squared. And the elliptic curve cryptography is ECC, is based on these kind of computations. Right? So what you need to do is, if you want to crack a private key, it requires to solve certain computations based on these kind of multiplication that I introduced here before. And all known classical algorithms are again exponential. That means we are safe by using elliptic curve cryptography. Full stop. We are considered to be secure. And the whole public key infrastructure makes ubiquitous use of these kind of algorithms, ECC, RSA. You know that TLS handshake, encryption, decryption, signature, cryptocurrency, right? Secure messaging, certificate. It's all dependent on these basic algorithms. That means if you break these algorithms, this will be a major hit on today's IT infrastructure, right? Basically, it will be gone, right? And this will have serious impact on companies. All your data are no longer secret. on governments, right? All our information that the government has about us is no longer secret. Public life, no online banking, no online shopping anymore. It will be gone. And is it possible to crack it? Unfortunately, yes. So we need to dive for a couple of minutes into quantum computing. So meet the qubit. First of all, what is a bit? We all know what a bit is. It has two possible values, 0 or 1. But a quantum bit can be true. And in quantum physics, you use this crazy symbol here. It's called a cat. Cat 1 is true, cat 0 is false, and the quantum bit is true and false at the very same time. This is crazy. It's the very same time. And we write it this way. We say that the qubit is a superposition of true and false. And you write it mathematically. A qubit Q is alpha times false plus beta times true. And because a qubit, at the end, when you manipulate a qubit, you want to measure what its actual value is. So you measure it, and with probability modulus alpha square, you measure false, and with modulus beta square, you measure 1. But because you measure at the end either a 1 or a 0, the alpha square and beta square sum up to 1, right? Because at the end, if this is the probability to measure 0, probability measure 1, because you measure either 0 or 1, they sum up to 1. That basically means a qubit is a vector of length 1. And graphically, you can represent a qubit by a point on this sphere surface of a ball of radius 1. And this qubit now has an infinite number of potential values. Not only this poor 2 values, has an infinite number, because any point on this Bloch sphere is the potential value that the qubit has at this very moment. Yeah? Okay. And as we can bundle together bits into a register, we can bundle qubits into a quantum register. Here we see n qubits. And this quantum register is also in superposition, but not of the 2 values, true or 1, but of this 2 to the power of n values at the same time, because each qubit could either be in 0, 0, 0, 0, this is this state here, or the first one can be in 1, the others in 0, this is this state. So you have 2 to the power of n potential values, and now you take the superposition of it. That basically means if you have n qubits, you have a superposition of 2 to the power of n values. Let's take an example. It is well known that the number of atoms in the universe is less than 10 to the power of 90. It's a huge number, 1 with 90 zeros. If you rewrite it into the power of 2, it means it's 2 to the power of 300. That means if you have 300 qubits, you can store the information that you can build if you turn every atom in the universe into a bit. Right? 300 qubits have the information content of the whole universe. And today, 300 qubit is okay. Right? Johanna and I, we are working with computers that have about 400. We use IBM's machine. Right? We have already 400 qubits. So the information that you can manipulate is incredible. Yeah? And all values are manipulated at the very same time. A single step manipulates all the information content of the universe and more. This is referred to as quantum parallelism. This is the first origin of power of a quantum computer, this incredible high degree of parallelism. And it gets even more crazy, because the real power is a miracle. And this miracle is called, here we have 2 qubits, and these qubits can be correlated to each other by a mechanism that we don't understand that nearly 150 years. It's called entanglement. Well, they are somehow correlated, right? And to give you an analogy, let's assume that the 2 qubits are 2 dice, right? So you have 2 dice, and let's assume the 2 dice are now entangled. What you can do is you can move the 2 dice apart. I stay here, you fly to Andromeda Galaxy in an arbitrary distance. I roll my dice, and as soon as I know the value that I achieved, I know the value that you have in your dice. This sounds crazy, but it's really crazy because it's at arbitrary distance instantaneously, in 0 time. That means there must be some communication faster than light. Einstein didn't believe it. So he invented entanglement as a counter-argument against quantum physics. because he said God doesn't throw dice, right? It can't be that nature is probabilistic. So he invented the entanglement to counter quantum physics, but in the meantime it has been proven, right? There are experiments. 2 years ago the Nobel Prizes were given to 3 people that in experiments have proven that this kind of phenomenon really occurs, right? And this entanglement can't be simulated on a traditional computer. It's absolutely unique for quantum computing, and you can prove that every quantum algorithm that shows an exponential speedup, and there are many quantum algorithms that show an exponential speedup compared to classical algorithms, must exploit entanglement. So entanglement is somehow the real origin of the power of a quantum computer. This is entanglement. Remember that the qubit is a point on this sphere of radius 1. Right, here is the qubit. If I manipulate the qubit, I produce a different state on this sphere, right? So I produce a different state. Where does it come? So here's the other qubit. That means I manipulate a vector of length 1 and result another vector of length 1. And such an operation in mathematics is called a unitary map. It's a linear map, a unitary map. And if you manipulate one, so it's a matrix. Right? And if you manipulate multiple qubits together, you have here a unitary transform, there a unitary transform. If you bundle them together, it's again a unitary transform. That means a series of unitary operations is again a unitary operation, and this is a quantum algorithm. A quantum algorithm is a unitary operation on a quantum register. This is very, very different from classical programming. If you program a quantum computer, you do mathematics. Mathematics in complex vector space, in Hilbert spaces, right? Remember that if you want to plan your skills to prepare yourself for quantum computing. Completely different paradigm, right? You need people who understand mathematics in order to program a quantum computer, right? And now we come back to this, now we come to an algorithm that a mathematician has invented, Peter Shor. It's a quantum algorithm to compute prime factors in polynomial time, exponentially faster. I will give you the real numbers in a couple of seconds. And in fact, Shor's algorithm is computing discrete logarithms. Not only RSA is in jeopardy, but also ECC. That means a future, not today's quantum computer can crack today's cryptography, right? That is based on prime factorization or elliptic curves, because both require to compute discrete logarithms. And it takes only days to crack RSA. Some people say, some estimations say it's less than a single day. But on ECC, although it's more modern, you only need a few hours, up to a single hour. Right? So this algorithm can crack what we think is secure today in a nutshell. So, and this kind of future quantum computer that is powerful enough to bomb us back into Stone Age is referred to as CRQC, a cryptographically relevant quantum computer, right? CRQC. And the question is, of course, we will discuss it, when will this happen? Frank, please keep me assured that it takes 100 years. No, it's extremely fast, right? So, and why should you take care today? Why am I here? To make you nervous. The reason is, many data that are secret and have to be kept secret for many years are encrypted with today's methods. RSA, ECC, beat the hell out of me. That means these data can be cracked in foreseeable future, in a few years. And that means we need quantum-safe procedures that can't be cracked by a quantum computer, and we need a software infrastructure that implements and contains quantum-safe algorithm. That means we need new encryption algorithms. And building this infrastructure takes many years. But in parallel, the vendors of quantum computers spend lots of money and effort and resources to build this kind of powerful computer. And what is happening as we speak is something that is called harvest now, decrypt later. Right? There are adversaries that steal your data without letting you know. They steal the data, store them, and as soon as the CRQC, a powerful quantum computer, is there, they decrypt the data and go to you and ask for money. Right? This is, some people call it steal now, decrypt later. This is currently happening. It's a severe danger. And the defense is something post-quantum cryptography. What the hell is that? It's centered around algorithms very different from prime factorization and elliptic curves. It refers to lattice-based cryptography. A lattice is a set of discrete points in a vector space, and you have two vectors here that span the lattice. Multiples of each vectors and combinations of the multiples form this kind of a lattice. And there are lattices defined, like RSA is defined, and what you do is the private key is this good basis. The good basis is nearly orthonormal, so the vectors are nearly orthogonal, have nearly length 1, and there are also bad bases. The length is very different, and the angle is very, very small between these vectors, and computation in the good basis are simple, computation in the bad basis are terribly bad, right? And how do you do encrypting? Encryption, what you do is you take a message and you transform a message by a well-known algorithm into a point W in this lattice. And if you want to encrypt, and you do this based on the bad basis, and if you want to decrypt it, you as the owner of the private key take the good basis, compute the closest point to the message W, do some rounding. The rounding algorithms are also published, and then you decrypt the message. This is in a nutshell, the real explanation takes some 30 minutes, how it basically works. This is how lattice-based encryption fundamentally works, right? And this means decryption, yeah, I said that, and all known algorithm, both classically and quantum. This is the good news. There's no known quantum, but also no known classical algorithm to crack keys in a lattice on this kind of algorithm here. So this means lattice-based cryptography is considered secure as of today, because we don't know any classical and no quantum algorithm to crack it. And this will have some implications that I will come to at the end of the talk. So post-quantum cryptography refers to cryptographic algorithms which, according to today's knowledge, are secure against attacks of a quantum computer or a classical computer. No known algorithm is known to allow to crack this algorithm, and most algorithms are not quantum safe. As I said before, factorization can be cracked, the elliptic curve can be cracked, any others too, but these lattice-based algorithms can't be cracked. But there's no guarantee in the sense, is there a mathematical proof that these algorithms can't be cracked? And the answer is no. It is not known whether some smart guy is sitting in his room and tries to crack algorithms, as I will reveal in a couple of seconds. They're currently standardized to crack these algorithms, which has impact on how the infrastructure must be built. We must have an agile security infrastructure, right? Okay. And NIST, the National Institute of Standards in the US, they are working on standards for post-quantum cryptography. They defined a process, 2016, to submit, evaluate, recommend standardized quantum-safe algorithms. And they have 3 published standards, and a couple of days ago, a 4th standard has been published. Here are the links. If you have the handouts, you have the links to these documents. Be aware this is pure mathematics. The standards are mathematics. You will get crazy if you open the 50-page document. It's only mathematics. And there's an industry consortium called PQCA, the Post-Quantum Cryptography Alliance. It has members like Amazon, Cisco, Google, IBM, NVIDIA, blah, blah, and many more that are written here. And they entertain 2 fundamental projects. One is called the Open Quantum Safe project. One is called the PQ code package. Different. I will work a little bit on Open Quantum Safe. Open Quantum Safe is an open source project entertained by the companies you saw before. And they are developing and prototyping quantum-resistant cryptographies. And they built a C library, an open source C library, liboqs, Open Quantum Safe. Open source of all these quantum-resistant cryptographic algorithms that NIST is standardizing. And they prototype by using these open source implementations in protocols like TLS and SMTP and so on. So they implement the algorithms for everybody to use, and then they fold it into the underlying protocols, right? That your SSH and so on are basically already made quantum safe as a prototype. Everything is in GitHub, so if you go to the web page here, on top you are pointed to GitHub and you can take a look at the code. And it's not only C, there are Go wrappers, Python wrappers around that if you hate C, right? So this is also, everything is open source available. And as I said before, lots of contributors, Amazon, IBM, Microsoft, Cloudware, and so on, they are all contributing to these open source implementations, which is good. But how do you become quantum safe? There are reports that in companies, significantly less than 50% of the business leaders understand that they are threatened. Right? It's very difficult, and if it's threatened, then they read in a paper about quantum computer and they think this is all science fiction, and then they don't spend money and say, okay, go ahead, we are not threatened. But in the government, for example, in the US, they already had a law, 2022, that says that every government agency must come up with a plan to become quantum safe in, I don't know, 3 or 5 years. I just forgot the number. So what they do is, their strategy is that the United States begin a multi-year process to migrate their vulnerable today computers to make them quantum safe. Right, this is the strategy, and you can follow on their web pages the status, everybody has submitted plans and so on. They are very open about that. You see what they are currently doing. Right, recently, in July 24, they published a report on post-quantum cryptography, and they recommend how to move forward, and they recommend all CEOs, and there was legislation under discussing. If a CEO knows that they are threatened and the company goes bankrupt because adversaries steal the data, encrypt everything, then the CEO might become in charge by his own private money. I didn't follow up whether this law has become, but they really take it serious. They would like to force all of the American companies to become quantum safe. And the cost they estimated last year was $7 billion in order to migrate only their government computers to become quantum safe. The European Commission is doing similar. There's a so-called roadmap for transition to post-quantum cryptography for all the countries, and the EU is investing in that. It's also ongoing. And companies are working on it. AWS has released a bunch of products that are quantum safe. Microsoft did that. Google does, for example, Google publicly speaks about that all their internal communication is already quantum safe. Right? So that means this harvest now steal data can't be done with Google. And for example, if you use Chrome, there's a flag in Chrome that you can switch on, and then the communication in Chrome to Google servers are quantum safe. So they take it all serious, right? You just flip it on, and you don't see any impact on performance. At least I can't see it. IBM does it, Cloudflare does it, and of course we at WSO2 do similar. So we already have a Ballerina version out that is quantum safe. If you build components in Ballerina and they communicate with each other, you can configure it such a way that the communication is quantum safe. If it comes to IS and Esgadio, the communication with IS and Esgadio is quantum safe. We store all the data in IS Esgadio to be protected against quantum attacks. So we are also doing these kind of things. You need to configure it. And as I said before, the infrastructure must be quantum agile, so to protect against failures of encryption procedures, because I said before, some quantum procedures may also be cracked in some future. And the new infrastructure must make it easy to exchange such procedures. So originally, NIST wanted to publish 2 years ago 4 algorithms in parallel. And they published the algorithm and said, these are the 4 winners of the first round. Now you are quantum safe, and within an hour, a group of cryptographists published an algorithm that cracked one of them. Right? So this was, they prepared it, right? It was well done. So this is the real threat. They are specialists in cryptography worldwide. They invent this post-quantum stuff, but again, there are also adversaries that try to hack it. This is why the infrastructure must be quantum safe. You must be ready to unplug an algorithm if it got cracked and plug another algorithm in, right? And it must be simple, right? And what people are using, we at WSO2 we also use combination of classical and new algorithms, right? So if we sign a document, for example, we sign it classically in addition with a quantum algorithm. So if one of both is basically breaking, right, the signature is still there by the other. This is also going on, right, that you use in parallel or in sequence mixtures of algorithms. Right? There is a report how you can do it, also published by NIST. And here is a very recent article that gives an overview, a systematic overview of what kind of mechanism, how can you become quantum agile, right? And this is a layman's version of the agile cryptographic infrastructure, right? There's an infrastructure like TLS, for example, and you use TLS with RSA, AES, Kyber, and Dilithium. Kyber and Dilithium are two of the non-broken post-quantum safe standards and others, and you can, in a round-robin way, protect your communication by this or in parallel, and if one algorithm fails, you unplug it and move a new algorithm in. And what NIST is doing, they published 4 standards, but it's an ongoing process. They published recently, a couple of days ago, another one, and their goal is every couple of months to publish new standards to protect all of us against quantum attacks if one of the formerly published algorithm basically fails. But how much time do you have? So assume T-collapse is the time, the number of years that must pass until we have this powerful quantum computer, cryptographic relevant quantum computer available. So some people say it takes 20 years, some people say it takes 5 years, many people say it's about 10 years. So early next decade, we will have a quantum computer that can break all of our infrastructure. With the announcement Microsoft did a few days ago that they have a quantum, that they have qubits that are absolutely stable, they say it's much earlier. Right? So if you believe this hardware vendor, they say 27, 28, it may be that we have a powerful computer that blows us all back to Stone Age. So T-collapse, how long is it? Then, if you are convinced by my little talk about that you must become active, then you kick off a project and you need the T-migration number of years to migrate your infrastructure to become quantum safe. And then you have the shelf time. The shelf time is the number of years you must keep your data confident, right? Secure. Typically, while you migrate to a quantum safe infrastructure, you produce information, and at the last day, you also produced information that must be kept secret for this number of years. And you are in trouble if the shelf time plus the migration time is less than the collapse time, because from that time on, all your data can be decrypted, right? And this is, you don't want to run into this situation. That basically means if you assume, so the time you have for your migration project is shelf collapse time minus shelf time, and assume that in 10 years we have a powerful quantum computer, and your data must be kept secret for 10 years. In many companies it's even longer. You have 0 minutes left to build your quantum safe infrastructure. You are already in trouble now, right? And what should you do? First of all, create awareness, right? It's a multi-year project, but it takes some time, some people, some money, so you must go to the board and convince them that they have to invest. You must convince the business leaders. You must assess the security demands of your data. Are you already threatened because your data must be kept confident for a long time? And be prepared, harvest now, decrypt later. Typically, people recommend to build an inventory of security assets. That means determine that security, the technologies that you use in your enterprise to keep your data secure. In parallel, it is wise to build what some people call a quantum center of excellence. That means a bunch of people that are experts in post-quantum cryptography and quantum computing. Remember, this is mathematics, deep mathematics, so you must have a special kind of skill. And you determine external dependencies. It's not only important what you do to keep data internal, but you have a whole supply chain of software that you use in your company. Right? You must determine the external dependencies. Then you plan your transition to post-quantum cryptography and crypto agility. You establish a security governance, right? Which algorithms did I use? Which one are still valid? And then you need to migrate, right? So it takes some time. And to summarize, I try to make you nervous, remind you the crypto infrastructure as of today is based on the hardness of a certain mathematical problem, a discrete logarithm. Quantum computers at some time in the future, midterm, long term, will crack these secrets. Lattice-based cryptography seems to be the rescue. And standards are already published, more are ongoing, under ongoing development. Open software is available that implement these standards. Quantum-safe infrastructure must be agile, and it's time to act now. That basically means I hope that I threatened you and you're a little bit nervous now that you need to think about these concepts. And if you want to understand more, right, here you can take, here's the QR code of a paper that Johanna have recently published. It gives you much more background on the politics, but also 30 pages of mathematics, right? So, thank you very much.